this part of Germany and for this part of the world, but overall the potential in terms of other forms of energy. So the blue bars is what is delivered worldwide in terms of electricity for the overall, but also for the electricity provision. But let's say the share hasn't changed too much. Nowadays we are talking about e-fuels, electricity, our battery-driven cars, also heat pumps for buildings. It will come, the blue bar, and its share will raise, but obviously this goes slow, and you also say that this won't turn around, that you still need other forms of energy. And what are those forms of energy? Those are fuels, like hydrogen, like hydrocarbons, but let's say where to take them from? This is the question. To make them green, you certainly need renewable energy. Do you have which potentials of renewable energies? You have different numbers here. The black numbers is a typical yield per area in here, and the red numbers is the overall potential in the so-called EUMENA region, which is Europe, North Africa, the Middle East, all the region which we consider, let's say, as accessible for energy demand and which have certain high capacity. Here, and if you compare the numbers, let's say for biomass, geothermal, wind and hydro, you have about the same order of magnitude in total capacity. A bit difference between wind and hydro, they have an order of magnitude higher than biomass and geothermal. But if you now compare to solar, then you go up again an order of magnitude on the area specific yield, but also in the overall yield, which means, let's say, whatever you do in the future, in order to make fuels or harvest energy in general, solar has to have a big part of it, maybe even the lion's share, to provide the green energy of the future. Looking into pathways for fuel production. In the introduction, we already heard, you have talked a lot on PV, wind is similar, you go to electrolyzers, this is rather this part here on the right-hand side, where you need electricity, which can come from PV, wind, or also geothermal. Today I'm looking a little bit more in the heat-related routes towards hydrogen and towards synfuels, which are rather in this part here. Solar energy not only can produce electricity, you also can make heat in different temperature levels from 100 to up to 2000 degrees Celsius to power different chemical processes, which can split water, which can split CO2, which can convert biomass. There's a lot of options around, and I will guide you through some of the examples. So this is a little bit related to the discussion we had before. This looks into a process to make synfuels. We did this in some of our projects, and we also made up our mind. For the moment, we are looking into point sources of CO2, of concentrated CO2, but is this really carbon neutral? Do we have, let's say, a closed carbon cycle? Here, like the colleague stressed before, our decision and our conclusion was we have to go into taking the CO2 from the air, at least if we go for fuel production, in order to be completely carbon neutral. So in some of our projects, we looked into the entire chain, from CO2 from the atmosphere into synfuel, which then can be used for different application in the mobile sector or in industry. This is open, or for chemicals production. This is also an option. This is one of the examples of one thermal process, solar thermal process, which is able to split water to make hydrogen, to split CO2 to make carbon monoxide, or to do both at the same time in order to make syngas. And syngas, you know, this is kind of an universal intermediate in order to make any fuel, to make diesel, to make kerosene, or to make chemicals, polymers even. There we are quite open from this intermediate product. So, and this is an example of a two-step cycle, which we have used a lot. This includes one endothermal high temperature step. Here we are talking about temperature above 1000 degrees C, which is powered by concentrated concentrated sunlight, for example, like a solar tower. This is one option. And by doing so, we release oxygen from the metal oxide. We gain a reduced form, an oxygen-lean form of the metal oxide, which then can split water by abstracting the oxygen from the molecule, incorporates it into the metal oxide lattice, and hydrogen or CO are left over as the product. And by that, you again have the oxidized form of metal oxide, and the cycle is closed. So, to do so, you have to concentrate the sunlight, you have to heat the material, you have to feed the feedstock into such a process, you have to do kind of a heat management of this, you have to control the process, you have to build a solar tower, you have to build the heliostat field, and take care of all those aspects and all those components in order to show that this is a feasible process. So quite a wide range from material science into engineering, into chemical engineering, into mechanical engineering, which we had to do in the last years in order to show that this is an efficient and functioning process. Let's look into the components. We have to concentrate the sunlight. There are different options, different shapes of mirrors. Of course, you need a mirror. To do so, there are line focusing systems, so-called parabolic trough, where you don't have a point focus, but rather a line, here a tube, which contains a fluid. It can be a gas, but mostly it's a liquid, like liquid oil. It can also be water and steam. Molten salt is also an option, which is heated by the concentrated radiation from this mirror area up to, in this case, around 400, 500 at the maximum. This is not an ideal concentration because the line focusing system is not ideal concentrating. You have to go to a point focusing system to get to higher concentrations. So we talk about, let's say, up to thousands of sun, 1,000-fold concentration of the sunlight, which allows you to go to much higher temperature. 1000 degrees C is absolutely no problem. In some of our processes, which I will show later on, we even go to 1500 degrees C. Here you see some examples. They are all located in Almeria, the so-called Plataforma Solar de Almeria, which is built up for demonstration purposes. This is operated by the Spanish organization CIEMAT, and DLR has a permanent delegation there in order to do projects, in order to do demonstrations. And similar, we have in Jülich, in the western part of Germany. There, this tower is located. There are also several thousands of these mirrors, of these heliostats located in front of the tower in order to do demonstrations there in the order of some megawatts. This is not yet commercial, this system here, but let's say for power production, you find several of those plants in the solar belt of the globe, where this kind of technology is commercial. For example, in Spain or in the US or in South America, you find those plants in commercial use. You need a reactor, which means you have to introduce your concentrated radiation in order to do a chemical reaction. This can be done directly, this can be done indirectly by using a heat transfer fluid. There are different options. One option is to use particles. Here we have inert particles. This is a project called CENTREG, a centrifugal receiver, which is shown here in this demonstration. Particles are flowing down in the inner part of the cylinder, which is rotating fast, and the centrifugal force is forcing the particles to the inner surface of the cylinder, where solar radiation is introduced from the mirror array to heat up the particles. And then the particles can be either stored, so you have an option for 24 hours operation, or the heat is transferred to any process, to a power cycle to make electricity, or to a chemical reaction. Or the alternative is to use reactive particles. That the particles shown here are, for example, the redox material I have shown before. This is one option to run such a process directly, which has pros and cons. Here is one example, a project which we do together with an American organization. This is funded by the Department of Energy, so Sandia National Lab and NDLR are departments within this project. And on the left-hand side, you see a reactor where particles are introduced and moved by a so-called slipstick plate. This is a kind of vibrating plate, which you know from industry, from minerals processing, for example, moving the particles through an area which is irradiated from the top by mirrors which redirect radiation top down, which has also some advantages. And this is the example to do this in two steps. And here, the metal oxides, so the particles are the metal oxides, they are fed from the top. They move through an irradiated area here from the first chamber to the second one, and then you have reduced particles which are then used in a second step to split water or to split CO2. This is another example. There we don't go via particles, we rather go through monolithic porous material. So the yellowish arrangement here is a ceramic foam. It's porous, it can absorb radiation which is coming from the front of this reactor. And in order to do in the first step the reduction, which I already stressed, the high temperature step. Here Syria is shown as an example for such a redox material which is capable of splitting water.